work, which has been collaboration with the Honda Research Institute from Japan. And today I'd like to how we improved our ultrasonic sensor to make it suitable for gesture recognition. Okay, did you ever wonder why our ear is so complex? You have a tragus, an antitragus, a helix, an antihelix, a fossa, a concha. It's a very involved shape. Well, is it a quirk of nature or is it really necessary? Well, it turns out that we use all these features to do elevation estimation, so they're very important to us. And so, in fact, a colleague of mine told me that we shouldn't neglect that our universe is kind of a big learning machine, which has been learning for so long, and that we should take that lessons into account. And that's why we also like to take inspiration from nature to see how we can improve our sensors. Okay, the application might be gesture control in a car to control your car stereo, but also might be in healthcare, for example, in an operations room, a surgery room, where a surgeon wants to control a certain device without touching it, such that he's not contaminated, right, and that he can continue his surgery. And so what we observe is that bats who are very good in using ultrasound to position themselves, to locate themselves, that they also have these special features in their ears. For example, you see also a tragus here, and you see it bigger in the enlargement here, but also you see these fine ridges in the ear, and also they have an importance. So apparently it's also important for the bat to have a very complex shaped ear. And that's the inspiration we used. So what we did is we took our ultrasonic sensor technology, and here you see a circular shape with 9 microphones. And what we do is we put baffles on top of the microphones, in fact, to mimic the shape of an ear. This is an overview of our prototype that we have. It's a stack of 3 PCBs, and I'm starting from the bottom. And the bottom is the board on the right, which is a communications board to get our data from the sensor into a computer. The second board is also kind of a standard board, is a microcontroller, an STM-F4, which we do to do the sampling and also to arrange the data such it can be transmitted on the communications board. And the top level is kind of a hat, which we can change for other hats, for other applications. And that contains the microphones, the 9 microphones, the golden blocks you see here, with some active bandpass filtering. Okay. Let me tell you about the working principle of the sensor. So here you see on the bottom, you see our sensor, and you see a number of reflectors here. And the cycle starts with the speaker emitting a chirp, which only lasts a microsecond, a chirp from 35 to 45 kilohertz. And of course, all those reflectors reflect a signal back to the microphones. Let's focus on a single microphone. Then this equation is a model of what the microphone receives. So the K microphone, that's what the superscript K stands for, receives the original signal, which has been delayed a little bit, and which also has been filtered because of the spatial directionality of the microphones, and of course also because of the baffles that we put on top of them. And so that convolution kernel will be heavily dependent on the azimuth and also the elevation or the complement of the elevation which we use here. And of course, it's the baffles that make that convolution kernel rich. Okay, to show you what I mean with making it rich, the top one is using no baffle at all. So it's just a circular opening on top of the microphone. And then you see that the main reception kernel is really located in the center, right? While if we put a baffle on top of it, then you see that for different frequencies, that focus is changed to a different spot because of all of the positive and negative interactions that happen between all the waves and all the paths that you have in the reflection. We compared a lot of different options for our baffles. And so, well, this is the one we chose finally to do our experiment on, because we thought from taking a look at the graphs that that was the best one. And so we chose to define our features manually, not to have automatic feature extraction or detection. And we use features from the time domain and the frequency domain. Let's first go into the time domain. So what we do is we bandpass filter the original received signal. We take the absolute value and low pass filter it to get to the envelope. And then from the envelope, we take the strength of the main echo and also the range, so the delay of the main echo. And those are two features for the first microphone. And so for every one of the K microphones, we put them one after the other into a time domain feature vector. In the frequency domain, we just take the discrete Fourier transform of the original received time domain signal. And then we look for the strongest frequency component in there. And we put the magnitude of the frequency component and the frequency of it also in a vector for the K microphones. Given the fact that we have 9 microphones and we have 4 features per microphone, we have a 36 in length feature vector. We do the measurement every 100 milliseconds, so 10 times a second. That gives us a feature vector, because we're measuring for 1.5 seconds, of 540 by 1. Okay, so those are the features. Let's take a look at what we actually did. We had 20 test persons perform each 80 swipes, going right to left, going left to right, going up, going down. And we put all the results of those measurements in a database. So we have 1,600 separate sweeps or swipes. That data we split into a training set, into a testing set. We took 1,000 samples from the training set and 600 for the testing set. On the training set, we tried to determine the main subspace so that we could project the training data onto the main subspace. And we use the same principal component vector to apply the coordinate transformation to also transform the test data to the subspace. And then using the training data, we trained a nonlinear support vector machine, a multi-class support vector machine, because we want to distinguish the 4 different gestures. Okay, and these are the results. In the left-hand confusion matrix, I only used time domain features, so I didn't use the frequency domain features. And so what you see is that the up and down gesture is recognized very well, because of course you're putting your hand on top of the sensor, and so the range, the time domain data changes significantly, and therefore it has a very good discrimination, right? While if you take a look at the left to right movement on top of the sensor, well, then the range data doesn't change that much, and therefore time domain data doesn't get you there. And that's where the spectral features really come in handy, because the spectral features make sure that we also can have a good recognition of the left to right gestures as well. Okay, so time for some conclusions. I tried to propose to you our new gesture recognition sensor, which is based on the fact that we use inspiration from nature to put baffles on the microphones to create a spectral rich feature set. Well, I hope that I illustrated to you that using the frequency domain features are really necessary to make the sensor work properly. We tested on 20 subjects, which is not a lot, I guess. And here I want to connect to the first speaker. We're also working on using simulations to improve on the sensor. But so our goal is to increase the gesture range and also increase the data set, partly using simulations, because that's very useful. Thank you.